Come on, there we go. We're going in as far as we can get. You should be on LearnSmart 7.4 and 7 to 7.6. So you should be on your second LearnSmart. So we're going to be doing a lot of things today. I'm going to give you your pre-lab today. I didn't get it out. The reason I didn't put it out is because I forgot to hit the staple button. So I'm going to be handing those out to you as we have some downtime here. That you'll need to get going on that because there's several different parts on that, so you'll need to do the pre-lab and be ready to roll on that. So we've got a lot of things we're covering today, so let's go ahead and get started. We ended last time, if I remember right, on this slide. Is that right? Yes? They're over here in CE Chem 1110 brown crate. So we finished on this one, is that correct? Okay, I'm hoping my board will let me write today. Yesterday it didn't, and it doesn't look like it's going to today because it's got no power. And I'm not sure why it doesn't have power. Try just doing this. Let's see if we can get it. Nope, it's not going to let me. Okay, so we're going to do a little bit of fiddling here to make it work. Bring up another one. Did we get to the second one, or do we just do the first? Did we do? Okay. All right. So I'm going to bring up another thing here, and I'm just going to do it from over here. So what you want to do on this one, remember that we've got copper metal as a density here. We've got two different temperatures that we're working with, and because of the two different temperatures, we have two different densities. So because of that, we're going to rearrange the equation again, and we're going to do two density equations where we find volume for each density at the different temperatures. So since this is density, we have a 10-gram piece. Remember that density is equal to mass divided by volume. So if we rearrange that, we're going to end up with volume is equal to mass divided by density. So as we put those in for each of them, we would end up with volume equals, our mass is always 10.0 grams, and we would divide that by, the first one, 8.92 grams per centimeter cubed, and we would get an answer. So if somebody would do that real quick for me, and I'll set up the other one for you. Volume is equal to 10.0 grams divided by the 8.83 grams divided by centimeters cubed. Whoops, cubed. Try it again. Okay, and somebody do the bottom one. Let's get those answers up here so we have a example here, and I'm sorry you have to do it this way instead of handwriting it, but at least you get to see it. I guess I should put parentheses around these. We should end up with what unit? Centimeters cubed. And a centimeter cubed, you need to understand, is a milliliter. Okay, so that's 1 centimeter cubed is equal to a milliliter. Okay, so what do we get? Top one, who's got it done? Should be like 1 point something. Yes, go ahead. 1.10? Say it one more time. 1.12. Okay, centimeters cubed. Okay, who's got the bottom one? 1 point, yes? 1.13. Okay, centimeters cubed. So the difference here, if we look at that, I'm going to scroll that up a little bit, is just what? If we just subtract these two away from each other, the difference is 0.01 centimeters cubed. Whoops, got it backwards there. That's okay. 1.01 centimeters cubed. Okay, so does that make sense? If I heat something up from 20 degrees to 100 degrees, is the volume going to be so extreme? Because we've got a piece of copper. Am I going to see that copper just grow? Not very much, but it is going to grow a little bit. Okay, so we need to be able to understand that. Okay, let's go ahead and go on to the next page here. This is kinetic theory. Kinetic theory is how do gases and things move. So as they move, gases hit the wall, and because they hit the wall of a container, they cause pressure to increase. The more they hit the wall, the stronger the pressure is. Okay, so we have here some bromine gas, and you do sort of need to be familiar with the color of bromine gas. It's sort of a red-brown, and it does hang around in pairs. I've got a short version of the kinetic molecular theory to help you remember. I call it the toddler rules. And when you think of a toddler, what things do you think about? Okay, so as you're thinking about a toddler and what they do, think about these rules, because a toddler is usually considered somebody under 5, and there are 5 rules. So that helps me to remember all of it. But it also sort of relates to what they do. So first of all, these are about particles in an ideal gas. And not all gases are ideal. But if they were ideal, this is what would happen. They have no volume. So because they're so far apart, they are considered to have no volume. So a little kid, 5 and under, doesn't have to pay for a ticket in a lot of places. You can just put them on your lap and they're good. Okay? They have elastic collisions. Have you ever watched a kid try to walk? They fall down, as long as nobody's looking, they get back up and they try again. Or they crawl to something and stand up again. They're in constant, random, straight line motion. So with that, what's happening here is they want to, they see something they think is cool, and they go the beeline for it. And they get there and they look at it for a minute, and then they see something else cool, and they beeline for it. So they're in constant, random, straight line motion. Kids don't seem to be attracted or repelled by anybody. They'll go up and ask you exactly what is on their mind. I'll give you an example. When my kids were younger, we went to the store, and they hadn't been exposed to a lot of people of different color. We had some friends that were different color, but I guess this had been bugging her for a while, and my daughter saw a black woman in the grocery store, and she says, "Mommy, how come she doesn't take a bath?" Oh, geez. They just say what they think. My son was with me when we were at a grocery store, and he hadn't seen very many people that were tattooed or pierced. And there was a guy there that was tattooed and pierced, and he says, his mommy is going to get really mad at him for writing all over him. So, they just say what they think. They're not really attracted or repelled. They just think everybody has the same rules. Okay, and they have an average kinetic energy related to the Kelvin temperature outside. And the way I think about it this way is little kids, if it's warm outside, they want to be outside, they want to be playing, they want to be running around, they want to have fun, they want to go down the slide, they want to go swinging. When it's cold outside, they want their blankie, they want to turn on Disney movies, they want to snuggle. So it's directly related to the temperature, how active they are. So these are the 5 what I call toddler rules. If you remember, there's 5 of them, and they have to relate with a toddler, what a toddler would do. Okay, so there's a little toddler sitting on his dad's lap. Okay, so think of them as you're going through a constant straight line motion. They see something they want and they go right to it. Yes? Kinetic energy. Okay, they're curious, so they go straight towards something. They aren't attracted or repelled, and they have elastic collisions and they basically have no volume. Okay, remember kinetic energy is directly related to temperature. And then we get to teenagers. Get real, right? So if toddlers are the kinetic rule for ideal gases, then we know when we get to be teenagers, it's a lot different. There's a different set of rules, and they're more real, right? So particles in a real gas, and I think teenagers for this, and you'll see what I mean here in just a second. They have their own volume. You need your own space. Somebody starts to get in your space, you get a little bit uncomfortable, right? You are attracted and repelled by people. So you like some people and you don't like others. And you found collisions are not elastic. You learned that in driver's ed, right? Now, how can I get real gases to act more ideal? Because we want things to be under ideal conditions in lab, and we want things to be able to be predictable. And real gases are really not predictable. So we want to get them to work like ideal gases. So when are teenagers most ideal? Summertime. Low pressures, because they don't have any tests. high temperatures, that's the summer, and in nonpolar atoms or molecules. And I think about this as I get to choose the group that I hang with. I don't have to go to a class with people I don't particularly care with. Okay, so these little mnemonics, or whatever you want to call them, little ways to remember things, have helped me. If they help you, great. If not, then you're going to have to find another way to remember them. Okay, so toddler rules, there's 5. Get real, 3. Okay, so teenagers, get real, 3. And then 3 ways to make real gases more ideal. That's summertime. So I need my space. They attract and repel. We've learned that collisions are not elastic. At low pressure, I can choose the group I hang with in the summer. High temperatures and low pressure. All right, so to define each of the following. Kinetic energy basically is the energy of motion. We use kinetic energy is equal to 1/2 the mass times the velocity. That's not volume, that's velocity there, squared. And it does increase with increasing temperature. Okay? The potential energy is the energy of a particle has to attract or repulsive forces acting as a result of attractive, or I don't think that's right. That should be the stored energy. Potential energy should be the stored energy. Sorry, that's my brain was talking to me. This one I think is down, should be down here. Let me see what's coming up next. It is attractive forces, and disruptive forces are the forces that are associated with it. This one should be more of the stored energy, the potential it has, and that potential energy is a result of the attracting or repulsive forces acting upon it. So it's more stored energy here. Again, cohesive, associated with the forces between particles. Disruptive is it's resulting because of the particle motion. So as I increase temperature, disruptive forces increases. And I'll know when you're done when you quit doing the head bob. And again, I apologize for having to come over here to do this. I've got to get the STS in here and see what's going on with my board. Okay, most of the head bobbing stopped. Are we okay to move on? All right. So what is the equation for kinetic energy? We already wrote that down hopefully before, but it's kinetic energy, or Ke, is equal to 1/2 the mass times velocity squared. It's not volume. So suppose that we have a toy ball and it's thrown in the air such that it goes straight up and then falls and is caught by the person who threw it. How would we describe the forces of what's happening? So as it goes up right here, what would this force be? What would we call this as it's going up? Kinetic energy. Right when it reaches the top, before it comes back down, what do we have? We've got potential energy. Right at the top is potential energy because it stops for a minute before it comes back down. So it goes up, hangs there for a second, and then comes back down. So I just remember if it's in motion, it's kinetic. If it's standing still, it's potential. So as it goes up, it's kinetic. As it hits the top, it's potential. As it goes down, it's kinetic. Okay? All right. Now we've got actual numbers here. So I'm going to bring back that paper and get a new script page here. So here we have, suppose 180 pound or an 81.8 kilogram halfback is running at a speed of 8.0 miles per second. Meters per second, sorry. Collides head-on with a 260 pound or 118.2 kilogram tackle running at 3.0 miles per second or meters per second. Which one will be pushed back? That is, which one has more kinetic energy? So if we remember from our equation, Ke is equal to 1/2 mass velocity squared. As we put in for the top one, we want to use the kilograms, so we're going to use 81.8 kilograms, and we're going to times that by Oops, I forgot the 1/2 at the first, so let's put the 1/2 in there. 1/2 and then times the 81.8 kilograms. And then we're going to have the velocity, which is 8.0 meters per second. And we're going to square that. So would somebody put that in their calculator and let's see what we got. We're going to set up the other one just the same way. So while you're doing that, before anybody gets it done, I'm going to try and put in the other one. Has anybody got any of those? Move that over just a little bit. The top one? If we don't have calculators, I do have those up here. Please feel free because we're going to be using them today. Yes, Valerie? It's going to be fairly big. 2017.6. Oh, 2017.6. Okay, and that is joules. Okay, didn't fit really good there. We'll try and... It's not going to let me. There we go. Okay, what about the bottom one? Whoops. It's time to clean up. Maybe we got the bottom one? It's not going to let me come on. All right, what do we get for the bottom one? It's not this number. 531.9. Okay, so we can see the top one, even though he doesn't weigh as much, is going to have more force. And so he's going to push back the bottom one, if we've got our numbers right. Did I have a second on each of those, or do we have different numbers? Are we okay? When I put these in, I usually do the squaring first and then times it by the other things. That way I don't square the whole thing by accident. Just a hint there. Okay, so let's go forward. Now you've got to sort of think this one through. So which would have the greater kinetic energy? Hydrogen molecule traveling with a velocity of 2v or a helium molecule traveling with a velocity of v? So again, we're going to bring up our little paper here and get a new clean sheet. We're still going to be using kinetic energy is equal to 1/2. Try that again, fat fingers. Mass times velocity squared. So here we've actually got to look up hydrogen is 1.008, right? And then we would take the velocity, which is 2v. Now this is more like math, where we don't really end up with an actual number. We're going to end up with something v. And then on the other one, I should have the kinetic energy capitalized there, sorry. Thank you. All right, so this one, we're going to go 1/2 mass velocity squared also, but this one, we're going to have 1/2, and we're going to take the mass of helium, and I believe that's 4.003 about, is that right? 28 something, anyway, close. And we're going to times that by just V. So, what are we going to get? Yeah, that's supposed to be 1.008. Thank you. The 2 here and the 2 here, these 2's will cancel out, right? You see that? So my answer here is going to be 1.008 V. What about the bottom? Well, the 2 will take this 4 and make it a 2, so I'll end up with like 2.0015. It'll round up to be a 2 here, and V. So I can see that the bottom one's going to have more kinetic energy. Okay? Did I do my math correctly?
Well, we have to square the velocity.
Thank you. We are supposed to square the velocity, so that's not going to be straight. Thank you for that. I knew I was doing something it was too easy. Okay, so our numbers are going to be a little bit off. What is the top one going to be? I can't do it in my head now since we got to square it. Throw it through, guys. What we got? Right? Because the 2's will still cancel out. So this 2 and this 2 will cancel out. Yes? Well, it's mass. Oh, I squared the mass. Thank you. I am really having a hard time this morning, I can tell. Sorry. Thank you for that. So let's fix that. Squared the wrong thing. So we're going to end up with a v squared and a v squared. And now my highlight is highlighting the wrong things. That's okay. Let's check the numbers. So we're going to have 1.008 divided by 2. So 0.0. Nope, 0.5. Somebody do that in the calculator. I'm dying. Yes. 2.016? Don't think that one's right. Is it? Are we making sure we're squaring? Because the 2 and, oh, that's right, because it's on top. So 2.0 what? 16? Okay, on the bottom, what do we get? On the bottom, it should be 2.0. So 2 to do the same number of significant figures. So these two are really close, but the top one will win on this one. So hydrogen will win as far as having more kinetic energy. Right?
So does the V stay squared at the bottom?
Yep. Because this square goes through to the V2. Get rid of these. Okay, we all right? All ready to go forward? So we're just using that same thing. Now, we do need to know this. If you don't have it written down, write it down. If you don't have all these conversions, because you will need them. Hint, hint. Put them on your 3x5 card if you do not memorize them. You will need PSI, which is pounds per square inch. You will need bar. You will need kPa. You will need millimeters mercury, torr, atmospheres, and inches mercury. So you will need all these conversions. These are just different ways to measure pressure. And she is definitely going to want you to know all the different ways. Okay? We're going to be converting for many of the things that we do throughout lab and throughout all these things to be able to figure out what we need. Okay? And yes, there's 3x5 cards here, and if you want to start adding and making your 3x5 card, it's always a good idea. We okay to move forward? Everybody got these conversions down? No. Okay, going forward. You need to be able to do a conversion. So here is what we're trying to convert right here. Whoops. 28.6 inches of mercury. I want you to use the conversions that you just wrote down and find out how much that would be in atmospheres, torrs, PSI, bars, millimeters mercury, or kPa. I do have them down at the bottom here again for you so you can see what's equal to what. But I want to see if you can do it by yourself real quick, and then we'll do a check and see if you've got it. While you're doing that, I'm going to pass out the lab stuff that I've got stapled so far and see if I've got enough for this class. The orange is your procedure. The white is what you're going to turn in online. And then if you have your medical form, I'll come back around and pick that up if you've got that signed. If not, you need to get that signed for next time. Because we'll be doing parts of this lab the next several days. So make sure you've got your pre-lab done by next time. So if you get done before, I just realized this period's all girls. That's the instructions. Yeah, well, it was supposed to copy on back to back, and it didn't. And it was supposed. I thought I pushed the staple button, and I didn't. And it was supposed to copy 2 pages to 1, and it didn't. Okay. All right. How we doing? Have we got those conversions done? I'm going to come around and pick up your medical form if you got it. 1 medical form, yay. Any medical forms here? Okay, 1 over here, yay. 2 over here, yay. Any medical forms here? Okay, so medical forms I have to have next time because we're going to be in lab. So if you don't have it done by next time, you're going to miss out and you're going to be behind when we get to lab. So, yeah. There's more papers over there if you need another paper. We're not going to do the whole lab in one day, so we're going to do parts. So you'll have a little bit of tomorrow, next time. You'll have a little bit of next time. You'll have a little bit of next time. So we'll be ready, yes. The pre-lab needs to be done by next time. So that's homework. No. Okay. All right. The pre-lab is not that hard, so it should be fairly easy. We might have a few minutes at the end. All right. How are we doing? Are we ready to check? To see if you've got these down right? Okay, let's go. Let's see what you did. If you didn't get those down, you might want to write this down. Also, here's a little hint. Yes, ma'am. Okay, so that's okay. Ask. When you set it up, so say that we wanted to, I'll grab another paper here. So say that I wanted to do bars. I would start with my 28.6 inches of mercury, and I would set up a factor label. So I would set up a line. Let's see if I can get this. I'm going to bring it up so you can see my tools here. I would just set up a line like this, factor label, and then I would, on the top here, what I want to get to was bar. Was that bar that I was trying to get to? Yep, bars. So I look down here and there's 1.013 bars. So I put 1.013 bar on top. What I'm trying to get rid of is HG, so I look here and there's 760 millimeters, inches. I need inches. So nope, it's 29.92 inches mercury, and that goes on the bottom. At that point, then I can take and I can cross out inches mercury with inches mercury. Then I just times this by this, divide by this, and I've got bar. Does anybody need me to set up another one? So it's just a conversion factor. I'm using all of these to put the one I want to get rid of on the bottom, the one I want to go to on the top. Okay, should we do one more? So let's go ahead and do the KPA right here and see if we get the right one for KPA. So I would take 96.8 KPA and I would set up my factor label. Whoops, I got a red one, that's okay. And on the bottom, I would I'd look back here for KPA. There's 101 KPA. So on the bottom here, I would put 101.2 3 kPa. And on the top, since I'm trying, whoops, I wasn't trying to, I put this one down. I'm sorry. Let's go back to here. Should be the 28.6 inches mercury. And this kPa, since I want to get to it, needs to go on top. And what I want to get rid of is inches mercury, which is this. So I would put that on the bottom. Whoops, it didn't go. 2.9 inches mercury. So I've got it set up again where if I cross out inches mercury, my unit becomes kilopascals. And we should end up with that 96.8 kilopascal. Any others anybody would like to look at? Are you getting the idea how it works? Okay? All right, so we're going to go ahead and go forward. When we talk about pressure, pressure is force divided by the area that it's exerted on. So collisions of gas particles on each other or against the wall, when they hit each other, that's the pressure. So as we look, as we look at different pressures right here, the force that we put in a specific area does give us the pressure. This one atmosphere is equal to all these different pressures. Now, you'll notice down here, this is not kilopascal, but this is pascal. So the difference is 1,000. So I times it by 1,000 just to get pascal. So if you want to add that to your things, you can. So when a gas particles collide with the walls of a container, they exert pressure. And that's what we get when we measure atmospheres, mercury, torr, psi. So think of it this way. If you are a dancer and you're sitting flat-footed, you have a certain force. That force is over that area that you're contacting the floor with. If you raise up onto toe, that pressure, that area is a lot smaller. The force coming down is still the same, but the pressure has increased. And if you go up onto one leg where it's just one small area, you've increased a lot. That's why a lot of ballerinas, their toes and that have a lot of problems, because that's a lot of force to put on toes that weren't meant to go that way. Okay, so this is how we're looking at it. So as we look at the kinetic theory and gases and the gas laws, if we have a closed container and it has a certain amount of pressure and temperature and volume, if I increase the pressure pushing down on it, my temperature increased and my pressure's increased, where my volume hasn't done anything. If I take and increase the volume, then I've increased the pressure to make that increase in volume at the same pressure. So if we look at volumes, and this is just, there's nothing really writing down right here, we're just using our heads right now. N is considered moles. So if I have 1 mole of some gas in here, I have a certain volume and a certain pressure. If I increase that to 2 moles, then I'm going to have twice the volume at the same pressure. If I increase it to 3 moles, then I'm going to have 3 times the volume at the same pressure. So, as we look at the states of matter, solid is usually in a grid. Liquids will tumble over each other. There's no real rhyme or reason to how they're together. Gases are very spread out, and plasma is spread out, and it does have ions. When we explain each of the following observations using the kinetic molecular theory, gases have low density. That's because they're far apart. Okay? They have no attraction because they're so far apart. It's like trying to date somebody here, you being here and trying to date somebody that's in Alaska or in Guam. It's really sort of hard. Okay? A gas always exerts a uniform pressure on all its walls of its container because it's going back and forth and hitting at random. Solids, liquids, and gases all expand when heated. That's because they go from a low amount of kinetic energy, and when you heat them, you give them more kinetic energy, and they start moving around faster and faster. That means their pressure is going to increase. Okay, it's just like having a bottle with a balloon on top of it that hasn't expanded at all, heating it up, and the balloon starts to blow up. You still have the same amount of gas in there, but now you've excited that gas. Okay? So, the following statements are best associated with solid, liquid, or gaseous matters. So, match the statement to the appropriate state of matter. So if I say temperature changes influence the volume of the state substantially, which one would that be? Solid, liquid, or gas? So influence the volume of the state substantially. That's always going to be gas. Because if I increase the temperature, it's going to really increase the volume. Think of that balloon on the previous page. Okay, in this state, constituent particles are less free to move about than in other states. What do you think? Solid, yep. Pressure changes influence the volume of this state more than any other of the other two states. Gases, yeah, because I can squish gases. I can't really squish anything else. This state is characterized by an indefinite shape and a low density. Liquid, yep. Okay, so hopefully you got, and gas, sorry. Indefinite shape and low density. Oh, liquid has a little bit higher density, so that's why I put gas there. But indefinite shape is also a liquid. Okay, going forward, characteristics of gas. Gases expand to fill any container. Okay, they have random motion, no attraction. Again, that's the kinetic toddler rules. Gases are fluids. Like liquids, they will flow. Okay, they have no attraction. Gases have very low densities, no volume, lots and lots of empty space. So as you're looking at it, going back from solid to liquid to gas, you need to make sure you're thinking about all this empty space in here between molecules. They don't like to interact very well, so toddler rules. Okay, liquids here have a little bit more space, but they're still really close together. They sort of tumble over each other. Solids are the most organized. Going forward, other characteristics. Gases can be compressed. So there's a lot of empty space, so we can squish them. Gases undergo diffusion and effusion. Diffusion is through a room. So like if you open up and put perfume on, it effuses or diffuses through the room. Effusion is through a small hole. So if I have a gas leak, I want to make sure that the effusion of that stinky stuff is good so I can smell it, but I know that I have a gas leak. Okay, so it effuses through the hole, it diffuses through the room. Okay, and that's because of the random motion that gases have. All right, going forward. Changes in size of a container. So when you're looking at a large volume, you have low pressure. The particles only hit the wall every so often. When I squish those particles down, and I end up with high pressure because there's a lot of more particles hitting the wall and hitting each other. And because they hit each other, it's like having a pool table and you've started the pool game. Okay? When you start hitting those balls, they go crazy onto all the sides. So in a smaller container, molecules have less space, so they hit the sides of the container more often, and this causes an increase in pressure. As the volume decreases, pressure increases. So you've got to think volume and pressure sort of go together. If I increase the volume, the pressure decreases. If I decrease the volume, the pressure increases. So they're directly opposite of each other. All right, so we need to learn some basic terminology. STP. STP means standard temperature and pressure. 0 degrees Celsius, or 273.15 Kelvin. We use the Kelvin scale because in the Kelvin scale we have never reached 0 and there's no negatives. And when we're going to do a lot of calculations, we need everything to be in Kelvin. So anything that we use in gas laws will be in Kelvin. You've got to convert it to Kelvin. To convert it to Kelvin, we add 273 to 2.15 to Celsius degrees. We need to be in atmospheres to do most of it. Some of them we can use other forms right here, as long as those forms cancel out. You'll see that in a minute. So anytime I say STP or you see STP in a problem, it means 273.15 Kelvin, and 1 atmosphere is what you want to use for the most part. Okay, moving forward. So again, you'll need conversions between Celsius and Fahrenheit and Kelvin and Celsius. The Fahrenheit scale just is no rhyme or reason. It just was made and they just said, okay, 32 degrees is when it does freeze on this scale and 212 is when it boils. Celsius scale, they did it from boiling to freezing. So they said freezing is 0, boiling is 100. They did even marks between those and then just extended it out both sides. But we ended up with having 0 on the bottom of a lot of the equations that we were using. And if you're a mathematician, you know something divided by 0 is undefined. So we needed to have a scale so we didn't have that undefined problem and the problem with negatives. So they made an absolute temperature scale, which is the temperature scale of Kelvin, and we add 273.15 to the Celsius scale to get that absolute scale so we can do the mathematics we need to. Okay, so in this unit, just remember, anytime you're given a Celsius temperature, change it to Kelvin right away. That's a big, big, big problem if you don't. Okay? And here's my always use the absolute temperature scale when working with gases. It's very, 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 very important. Okay, so we're going to convert really quickly from Kelvin to Celsius here. Let's see what we can do. To go from Kelvin to Celsius, what do you think we need to do? Yes? Okay. All right, so what do we need to do to go from Kelvin to Celsius? Well, you're going to subtract 273.15. So if you subtract 273.15 from 78, you're going to end up with a negative number, right? And what is that negative number? To go from Celsius to Kelvin, what do you need to do? Add the 273.15. So go ahead and do that. Let's see if you end up with the same number I do. Again, if you don't have a calculator, please get one because we're going to be using it a lot. I might give you a brain break here in a minute just to do some of your pre-lab, but we need to get to a specific part. Good. Yeah, that is the right answer there. So these are not hard. Now, if I were to doing significant figures on either one of these, the top one I should have negative 195. Yes. It should be in Kelvin. Thank you. Yes, that should be in Kelvin, not Celsius. Whoops. So yeah, pretend that's a K. I can't change it right now. We'll put a little note in to change it, though. Thank you. All right, so next thing. We're now going to go into the gas laws. There are a bunch of them. I'm going to try and teach you with mnemonics that helped me. So the way that I remember the ideal gas law, it's a little bit weird, but it works, okay? Ideally, you're not a pervert, right? The ideal gas law is PV equals nRT, perv nert. So ideally, you're not a perv nert. Okay, where the ideal gas law, P is pressure in atmospheres. It has to be in atmospheres. You have to use the conversion factors to get it into atmospheres. Okay, it has to be in atmospheres. Where volume is in liters. So if it's in anything else but liters, you have to convert it. Where N is the number of moles. Where R is a constant. And the little things fell up a little bit farther, but that's your constant right there. If you remember your constant or put your constant on your 3x5 card, you will always know what units Pervnert needs to be in. And temperature must be in Kelvin, so make sure that you always put temperature in Kelvin. So we can solve, given any of these other things, 3 of the other things, we can solve for anything else on here. We could solve for pressure, for volume, for moles, for temperature, given the other 3, because R is always a constant. This, if we remember this law, we can get 3 other laws very easily. Actually 4 other laws very easily. But you've got to remember this one. Okay? And you've got to know the units. So the next law, are we okay to go forward? Okay, so let's go through an example. So how to carry out calculations with the ideal gas law. If we have a problem that says how many moles of gas are contained in a typical human breath. And I don't think you guys have this example written down, so if you want to put it on a different piece of paper, you're welcome to, because I did add those after. You do have it? Okay, awesome. The first step is to identify the known quantities. If you've ever done story problems before, I hate story problems, but if I take and I pull out things as I read it, okay, so how many moles? N, question mark. Okay, R of gas are contained in human breath. That takes, there's a volume, V equals 0.50 liters of air. And there's a pressure, 1.0 atmosphere, so P equals that. And a temperature, I need to change that temperature right away into Kelvin. That's the first thing I do when I'm writing it down. I change that temperature into Kelvin so I don't get tempted to write it as, in the problem, as Celsius, because it has to be in Kelvin. So I'm going to write down my knowns, and I do know I have R all the time. So R is a constant that I know. I'm trying to get to N. So I know it's PV equals nRT. So I'm going to, like I said, first thing I do is convert that to Kelvin. So now I have Kelvin. Okay. And I can plug everything in. So I'm going to I like to solve before I put stuff in for what I'm trying to solve for. So I like to set things equal to N. Some kids like to just plug everything in and then solve for N. Doesn't matter. You can choose which way is easier for you. I like to do that and then just plug in and make sure everything cancels so that that liter, by the way, should cancel. I forgot to cross that out. So pretend like that liter's crossed out right there. And then you just times to the top, divide, parentheses, times to the bottom, close parentheses. And you should end up with 0.02 moles. So it's just a matter of plugging into, this unit is nice that way. You are going to be given several different gas laws, and all you have to do is just plug in, but you need to know which one to grab. Okay. And the lab that we're doing is going to go through each one of these. I think each of the laws that we're going to be talking about. Yes. R is this down here at the bottom. The 0.0821 liters atmospheres divided by mole Kelvin. Okay, does anybody have any problems with doing this? We're doing okay? All right, like I said, I'll put this back up on your canvas too, so if you want to go back over it, you can at a slower rate. Okay, we're going to go to a next law. This one, you actually take the ideal gas law and you solve it for R. And then you say, I'm going to have 2 different, because R is a constant, R does not change. But I'm going to have a gas at 2 different situations. And I want to solve for something else. So my R's are going to be set equal to each other. And we get what's called the combined gas law. And the combined gas law just combines 2 different scenarios where they're both set to R. Remember I told you can get all the gas laws or a lot of the gas laws by knowing Pervnert. So Pervnert, if you solve for R and set it equal to each other, you get what's known as the combined gas law. Now a lot of times we don't change the number of moles of gas that we have. So a lot of times the N's will drop out. So it'll just be P1V1 divided by T1 equals P2V2 divided by T2. So we can drop the N's out if they do not change. So we get this. So the ends don't always have to be there. Okay? If we hold the moles constant. All right, so the next one that we're going to do as far as laws, and I'm not going to go through an example of each of the laws because it's basically pull out, label, and do. Plug in. Okay, so Boyle's law, to me, I think something's boiling over, right? Boiling over has to do with temperature. So Boyle's law actually holds temperature constant. So temperature goes away from our combined gas law. It's just the combined gas law, but temperature drops out. And of course, N could be there, but usually we drop that out too. Usually we hold moles constant because that's sort of hard to change. Okay? So P1V1 equals P2V2. All we're doing is changing either a pressure or a volume, but we're holding temperature constant. All right, so here's what we would do for this one. An example, you've got 4 liters. Again, I would say, oh, that's a volume. I'm going to call that V1. Of helium gas has a pressure, that's a P1 because that's tied to this. Now that's important. A lot of times they'll give you a pressure and a volume, but the volume will be for the second one. You're trying to find the volume for the first one. So make sure that the volume and the pressure tie together. So here it does. If this has a pressure, so these two tie together. So V1 and P1, what pressure, P2, does the gas exert if the volume is increased to V2? Okay, so I've listed all my known quantities and what I'm looking for. That's a big thing. It's a story problem. You've got to pull out what you need. Then you look and say, okay, well, I've got P1V1, I've got P2V2, that's Boyle's law. So I'm going to set up Boyle's law and I'm going to solve it for what I'm missing. Again, if you don't want to solve it here and you just want to put the numbers in here and then solve, that's okay too. Okay, I plug in and solve the problem. So 10 times 4 is 40 divided by 6. Liters cancel and we get 40 divided by 6 is about 6.7, something like that. I didn't put the answer, I'm sorry. Because 42 would be 7, so it's just under 7, right? 6 times 7 is 42, right? You guys are so helpful. Okay, so Boyle's law, the application here is when we're breathing. So this is a medical chemistry class, so we've got to talk about this. To inhale, the rib cage expands and the diaphragm lowers. This increases the volume of the lungs. Increasing the volume causes the pressure to decrease, and because the pressure is decreased, air is drawn into the lungs, okay, to equalize the pressure. So that's how our diaphragm works. To exhale, we contract or squeeze our lungs, and the volume is decreased. That forces air out, and we're able to expel. So that's Boyle's law. The next one is Charles. And when I think of Charles' law, I think of Prince Charles, or he hasn't been kinged yet, right? So Prince Charles, he's under a lot of pressure. His mom wants him to do certain things and do certain things right, and sometimes he does and sometimes he doesn't. But I think it's a lot of pressure. So I think he's under constant pressure. So pressure in our combined gas law is going to drop away. And we end up with Charles' law. Again, N could be there, but it doesn't have to be. Okay? So this is Charles' law. Again, temperature, really, really important that it is in Kelvin, because look at where temperature is. It's on the bottom. If I leave it in Celsius and I have a 0 on the bottom, then it's undefined. And if I have a negative, it makes my volume negative, which is not good because I can't really have a negative volume. Yes? Always Kelvin, always. Okay, just remember, always add 273.15 to it, get it in Kelvin, get it in the absolute scale. So this is the application of Charles' law. So the same number of air molecules occupy a smaller volume, giving the cool air higher density. Warmer air arises because it needs more volume. Excuse me. So heated air expands, Charles' law, so that its density decreases and hot air rises. So you can see that going over there. Okay, so this is another law, and it's called Gay-Lussac, or Gay-Lussac's, but I think of it as Gay-Lussac's, and let me tell you why. Okay, SUGS has to do with volume. So in our law here, volume would be held constant, and it drops out. Okay, these were just the guys' names. They were French that discovered this. Again, N could be on the bottom, but it doesn't have to. Again, this is very, very important that temperature be in Kelvin in this law, because we don't want a 0 on the bottom or a negative number on the bottom. We can have negative pressure, but it's not really great. That would be more like a vacuum. Okay, we okay to move forward? Then we get to Avogadro's hypothesis, or Avogadro's law, also known as. Equal volumes of gases at the same temperature and pressure have the same number of molecules. V and N are directly related. So 1 mole is equal to 6.022 times 10 to the 23rd molecules. We've done that before. But it's also equal to 22.4 liters. This means, for example, that the number of moles goes up, the volume goes up. Okay? If we hold some things constant. In other words, temperature and pressure. So if we were to write this one would be V1 divided by N1 equals V2 divided by N2. And I don't think I've got that written anywhere. V1 divided by N1 equals V2 divided by N2. I've got a form of it in a couple slides, but I didn't write it down. Okay, so this is still using our PervNERT. We're just holding pressure and temperature constant. So 2 of them drop out this time. So basically it's saying, Avogadro's hypothesis was basically saying, oh, if I have a mole of nitrogen and a mole of helium at standard temperature and standard pressure, then the volumes are going to be 22.4 liters. They're each going to contain 26.02 times 10 to the 23rd particles, but they're going to have a different mass. Okay? So it's just like saying if I have 24 elephants versus 24 mice, they're going to weigh different, but I still have 24 of each. Okay, molar volume, same thing here, just a different picture. We're just going to ignore that because I forgot to take the volume off or the sound off. Avogadro's law here. This is sort of what I did. Was telling you before, V1 divided by N1 would equal V2 divided by N2 because it's equal to a constant. If one increases, the other has to, kind of thing, because they're always constant. Mm-hmm. We'll take a break here in just a second, because I know I get bored after a while. Okay, so going forward here, Avogadro's law, if you look at the cylinders again, we talked about the cylinders earlier. Oh, I did have it. There we go. There's your Avogadro's law, initial conditions versus new conditions. Basically, if I times 1 by 2, I have to times the other by 2. So 1 to 1 becomes 2 to 2 because they have to be equal to each other. Okay, Avogadro's law, again, has to be at STP, 1 atmosphere, or 273 Kelvin. 1 mole of any gas is 22.4 liters. So this becomes important when we're working with equations. So remember stoichiometry? We can't just go from grams to moles to molecules now. We can also go, if you look at the back ones right here and these ones right here, not the front one, we can also go down now to where it's the volume at STP. So we can use a balanced equation now to actually find the volume of the gas given off at STP. And we're going to be doing that in lab. All right. So how to convert Avogadro's law. So here we have 2 liters of N2, the original quantity, how many at the desired. We have this. We go through, we say, okay, which conversion am I going to use? The 22.4 over 1 mole or 1 mole over 22.4. I'm trying to get rid of liters, so put 22.4 liters on the bottom and I can find out how many moles I've actually got. So very simple stoichiometry. We've done this before. The only difference is we're just adding one more new conversion, and that's from the mole going down in those ones on the back 3 walls to STP. Okay? Any questions or problems with this one? We've got 2 more laws, and then I'll take a break. Next one is Graham's law. I think of it as Grandma's law because it has to do with how fast molecules move. And I don't know about you, but my grandma used to wear a perfume that was very heavy. And if she'd visited our house and left, and I came back from school and she'd already visited, I knew she'd been there because the smell was still there. Okay? So the MM here is the molecular mass. Okay? So, and it's opposite. So the rate of A divided by the rate of B is equal to the square root of the mass of B divided by the molecular mass of A. And it just compares how fast molecules move from each other. And we're actually going to be doing this in lab. We're going to be comparing two different molecules and how fast they move compared to each other. So Graham's law, think of Grandma's perfume. That's how I remember it. We've got Graham's law written down. Okay, this is the experiment we're actually going to be doing. We're going to take ammonia and hydrochloric acid. We're going to use Q-tips instead of plugs, so they're easier to use. And we're going to put them in here. The hydrochloric acid will turn into hydrochloric gas. We're actually going to be using ammonium hydroxide here, but it turns into ammonia gas. And where they meet, there becomes this white ring. And the first appearance of the white ring, you mark it. This one is expanded a little bit, so it's too big. But you mark at the first site of the ring. And then you measure from here to here and from here to here, and you can get the ratio going experimentally, which is pretty cool. Graham's law has to do with effusion and diffusion. We already talked about effusion and diffusion, but let's talk about it one more time. Diffusion is how it moves throughout the whole room. Effusion is how it moves through a pinhole. Okay? So diffusion is more like a mixing of the air out here, and effusion is through a hole. Okay. The last one that we're going to talk about before I let you have a little break here is Dalton's. Dalton's law of partial pressure. And I think Dalton is duh. Because, man, I wish I was alive and got credit for this law, because it's one you're just going to go, well, duh. Okay? This one is, if you have a total pressure, it's equal to all the little partial pressures added up. Well, duh. If I want a total, then I'm going to add up all the little parts, right? Well, we use this law a little bit differently. We're going to use it in lab this way. We're trying to find the pressure of the dry gas. When we bubble gas through water, some of that water turns into water vapor. So we have to take the pressure of the water away from the total pressure in the room to be able to find the pressure of the dry gas to be able to do the calculations. So I think I've included in your lab a tab in the orange salmon colored part, a table that has water pressures on it, but you can also look it up online for pressures. And you look on the table in Celsius. This is the only one you use Celsius to get the pressure of the water, and then you start working in Kelvin. So this is an example problem. With the following partial pressures, what is the total pressure of the sample? Well, you just add up each of the pressures and you get the total pressure. So that one's not real hard, right? This plus this plus this plus this equals a total. Now, it can be, here's another little trick, and I'm going to turn off the volume here for a second. This is really good. So if you put it on your 3x5 card, and you're looking and seeing if you've got the right answer before you put it on the test to plug in your answer. And you say, okay, I have pressure held constant, so I'll hold the P constant. Then if I'm moving temperature and volume, if temperature moves up, volume will move up. If temperature moves down, volume will move down. So you put your hand on what you're holding constant. So let's see what happens here. So if I move forward in this.
If we imagine holding temperature constant and raise pressure up, we would notice that volume would decrease. This is the relationship Boyle came up with. Pressure is related to 1 over volume. If we hold volume constant and increase the temperature, we notice the pressure will go up. If we hold pressure constant and raise up volume, temperature goes up. This will.
So see how these all work? So I'm holding temperature constant. It sort of pivots around temperature. If I hold, if I held volume constant. So it just is a really quick, did I get the right answer? This is just a really quick way to say, okay, if I'm looking for the second pressure and I'm holding volume constant and my temperature went up, then my pressure should have gone up. If it didn't, then I did my calculations wrong. So it's just a real quick check for when you're on the test. Okay, so going forward here, we'll come back and do these together in just a minute. I'm going to give you 5 minutes just to work on just to do some stretching, work on your own stuff, talk for a minute, because I know I need that break too. So you can work on your pre-lab, you can talk, get done what you can get done. I'll open up the computers so you can do, if you want to do that, you can do that. Learn smarts, whatever you want to do. I'm trying to get done with all of the lecture real quick for you because I'm going to have to take Friday the 1st off. Well, actually, that's after your test, so that doesn't matter. But I want to make sure we have enough time to get stuff done. Okay, I'm going to pause this video. Hopefully, if I can find out where it goes. Or not. Maybe I'm not pausing it. So if you're watching it online, you'll have to fast forward. So at 22, we'll come back for the last 10 minutes and work real hard and then go forward. If you need to get up and walk around for a minute, stretch your legs. Hello. Yes. Top drawer. Okay.
Because I'm trying to keep everything clear, you know what I mean? What's that?
Our both basketball teams won, so I had to have to bring it to cut out. Okay, sounds good. Okay, about another minute, we'll come back together. Hopefully you've been able to get some work done on your own or with your group. Okay, let's go ahead and get back together here so we can get some of this cranked out and hopefully give you some time to work on your Learn Smarts and stuff in other periods. So we're going to go through some example problems, and I'm going to show you how I do the example problems myself. So as I'm reading, I say, okay, a 200 milliliter, I've got a volume. So I put V1. Oops, let's see if it's going to let me go there. V1. And I write down 200 milliliters. A sample of oxygen gas is collected at 26.0 degrees Celsius. Oh, that's a T1. And I need to convert that really quickly to Kelvin by adding 273.15. And I will get 299, is that right? 0.15. Okay. All right, next thing, and a pressure, P1. Whoops. P1 equal to 690 torr. Ooh, okay, I might have to change that. I'm going to keep that up for a minute. What will the volume be? Okay, I'm looking for V2. Will the gas occupy at STP? So STP, let's see, I'm going to have a pressure that's constant, and if I choose the torr that is equal to 1 atmosphere, then I can cancel it out, I can use it. So what would the torr that was equal to 1 atmosphere be? Isn't it 760 torr? Whoops, try it again. Okay, and then the last part would be the temperature, and temperature 2 would be my standard temperature, which is 273 K. And I could put the 0.15. I should put the 0.15 there too. Okay, so I've got everything that I need to be able to go through. I'm going to just shrink that up a little bit. Whoa. Okay, let's try that again. So I can see everything. All right, so now what I'm going to do is say, okay, what law am I going to be using? Well, I don't need N, but I've got I need two volumes, I need two pressures, I need two temperatures. This is the combined law, because it has everything except for N. Remember I told you sometimes N would drop out. So this is the one that I'm just going to try and draw it real quick. V1, let's try a little smaller thing here. V1, P1 divided by T1 equals P2, V2 divided by T2. And I am looking for V2, this one right here. So if I rearrange it, V2, sorry about the drawing right here, V2 is going to be equal to P1, V1, T2, because the T I times both sides by, divided by, that's a 2 by the way, divided by T1 and P2. Okay, so now plugging in everything, so V2 would be equal to P1, which is 690 torr, times by V1, which is 200 milliliters, times by T2, 273.15 K. And I'm going to divide that all by T1, which is 299.15 K, times by P2, which is 760 torr. Okay, on this one I need to make sure that I put a parenthesis on the outside and the outside of here, so I make sure that when I times it through I've got it. So double checking, making sure my units cancel out. Torr cancels with torr, Kelvin with Kelvin. So as I times through I am going to get milliliters, which is what I want. So my V2 will equal some amount in milliliters. So if we plug this through real quickly on our calculators, I got 165.7, so 166. Whoops, I put it on the back side of that. 166. Is that what everybody else got? Okay, and if it were too significant, or one significant figure, then I'd really be in trouble because it would be 200 again. Okay? Am I missing something? I am. That clock in the back is bad. Okay, all right, so there are some practice problems here. I would like you, if you can, just to go through a couple of them, see if you can figure out what the laws are there, and then we'll do a balloon riddle next time. But we'll try and get to where we need to go over those examples. Hopefully we'll be able to write on the board this time.